Okay, this is the beginning of chapter 8, and it really kicks off the statistics portion of this course. So the title of the chapter is Statistical Intervals for a Single Sample, but we typically would normally use the phrase confidence intervals. And so when you hear me say confidence intervals, or if you see me abbreviate something with CI, I'm talking about a confidence interval. So let's get into it here. Suppose that I don't know the value of a certain population parameter. Like, for example, this section or this particular video is about doing a confidence interval on a population mean. So in other words, we don't know what the population mean is for a particular population, but what we're going to do is we're going to take a sample from that population and use the sample mean and our assumed standard deviation in order to get upper and lower bounds that perhaps capture the true population mean with a certain level of confidence. So that's where the word confidence comes in. So there are three types of confidence intervals that we can do on the mean or on anything really. The first is what we would call, this is what we would call a two-sided confidence interval. That's where we get both an upper bound and a lower bound estimate on the confidence. When you see these hats, these little, hats above the L and the U, this hat means estimate. And so this is a two-sided. This is what we would call a one-sided lower confidence interval bound because we're only interested in the lower bound. This is what we would call a one-sided upper confidence interval because we're only interested in the upper bound on that. And again, what we're going to be doing is basing it on a sample of lowercase n, that's the number of items in the sample. And again, these are going to be just estimates. Now, the other thing I needed to point out is when we get these upper and lower bounds, we're going to be able to say that they are a certain percentage confidence interval. And by saying that, we're going to say that it has a probability of 1 minus alpha, and I'll get into what alpha is later on, that the confidence interval will contain the true value of mu. Remember, we don't know what mu is, so we're trying to actually capture it. So L hat and U hat, both of these are numerical values. And so, for example, we might be asked for, typically what you're going to see is here's an example, find a 95% confidence interval on the population mean. That's what you might see in a homework problem. Sometimes you'll also see it as 99%. Those are the most common confidence intervals that we use. And so the way this 1 minus alpha relates to 95% is as follows. So 1 minus alpha times 100% equals 95%. So what that would mean is that alpha in this case equals 0.05. If we had a 1 minus alpha times 100% equals 99, a 99% confidence interval, well, that would mean that alpha is equal to 0.01. So that's how we will be referring to confidence intervals. Now I need to teach you some notation, and the notation is as follows. It is about the standard normal distribution. Now we learned about this in chapter 4 a little bit. We learned about what a standard normal random variable is. I'm going to change pens here just for something different. So when we talk about capital Z, so I'm going to write, that's an uppercase Z, is a standard normal random variable. And again, you learned about this in chapter 4. And what do we know about a standard normal random variable? Well, we know that the expected value of Z is equal to 0, and we know that the standard deviation of Z is equal to 1, and that's because the variance of Z, which we often call sigma squared of Z, is also equal to 1. So you're already familiar with this distribution. Now, what you're going to see in this chapter is you're going to see this notation. Now, these are all LC lowercase because they are actual numerical values. Remember, if it's an uppercase, it's a random variable. If it's a lowercase, it's a specific numerical manifestation of that random variable. So when we see z sub alpha over 2 right here, that is the value on the z-axis right here, such that the area above it, and that's the key word there, is above it, is equal to some value alpha over 2. That would mean that the remainder below it would be 1 minus alpha over 2, because the whole area from minus infinity to positive infinity has to be 1. So that's what that looks like right there. Now, if you see z sub alpha, and the reason that we're doing alpha over 2 and alpha is it depends on which one of those confidence intervals you're interested in. So you're going to be using z sub alpha here if you're doing one-sided confidence intervals, and you're going to be using alpha over 2 if you're using a two-sided, or you want to develop a two-sided confidence interval. That's why we're learning these two things. So z sub alpha, it's no different than the z sub alpha over 2. It just means that it is the value on the z-axis such that the area above it is equal to alpha, and thus the area below it would be 1 minus alpha, again, because the total area has to equal 1. And so here's an example. So for example, if I have z sub 0.01 is the value on the z-axis for a standard normal random variable such that the area above it here is 0.01, which means this area is 0.99. Now, it really doesn't matter what alpha is here. In general, alpha would be 0.01. So usually we would use 0.1 for a one-sided confidence interval. But if this was for a two-sided confidence interval and 0.1 was alpha over 2, then we would know that alpha was 0.02. So it really just matters what the area above is for the subscript and how you're applying the z value. Now, how would we get this particular value? Well, we can get that by using our inverse norm function in our calculator. So for example, this is z 0.01. That is the value such that the area above is 0.01. Now in my calculator, which is an old school TI-84 with some pixels that are definitely on their way out, kind of looks like a Trojan horse, doesn't it? So if I wanted to get this value on the z-axis such that the area above was 0.01, my calculator requires that I give it the area below. Now, you may have a calculator that has one tail or two tail possibly. I would recommend that if you have the calculator that gives you the option of the upper tail versus the lower tail, that if you want it to match all the work that I do in these videos, that you set your calculator, if you have the option, some of the TIs have the option, as I said, of left tail or right tail or lower tail or upper tail. I'm going to recommend that you set it to lower tail, because then you'll get the same numbers I do. So now I'm going to use my inverse norm function. And then my first argument has to be the area below the value that I'm looking for. So the area below here is going to be that 0.99. So it'll be 1 minus 0.01. Then I have to give it the mean. Just a reminder, this is how my calculator works. Area below the value that I want. Then we have a mean. So the mean of a standard normal random variable is equal to 0. And then I have to give it the standard deviation. And that's also equal to 1. And so when I do inverse norm 1 minus 0.01, 0, and 1, if I use that in my calculator, I will end up with, well, here, I'll show you how to get it, just like this. And I think you can see this one pretty good. It's decent. So if I go to second function, distribution, you've done this in the past, I go to inverse norm, and then I give it 1 minus 0.01 for a mean of 0 and a standard deviation of 1 it gives me 2.3263. So this value here is 2.3263. Now, we can verify that if you want to know if you got it exactly right. We know that if I integrated from negative infinity to 2.3263, I should get 0.99. Or if I integrate from 2.3263 to positive infinity, I should get 0.01. So let's just do one of those just to verify that what I just did was correct. All right. So if I did the integrating function, which is the normal CDF, and let's just go from 2.3263 up to comma infinity, which I'm going to estimate by 10 to the 99th for a mean of 0 and a standard deviation of 1. I'm going to get something very close to 0.01 here, and I do. So try it yourself using that normal CDF and go from negative infinity up to 2.3263, and I think you'll see that you'll get 0.99. You're going to be very familiar with this value very, very soon, I hope. So here's some of the typical z sub alpha over 2 and z sub alpha values that we will be using in this particular section of chapter 8. So the first one, let's go ahead and do a couple of these here. How about z of 0.05? So that means, again, that the area above here is 0.05 and the area below is 0.95. So if I wanted to get z of 0.05, I would do inverse norm, area below 0.95 for a mean of 0 and a standard deviation of 1. And what I will find, since I'm running out of room here, is that will equal 1.6449. Suppose I wanted, suppose I had a z, and there should be a negative sign here. Use the black marker here. So this would be negative z at 0.05 over 2. Remember, because this is 0, so this would be negative. What this means here is that the area below, sometimes you'll see this, that the area below is 0.025 here, and that if it was a positive value, if this was z of 0.05 divided by 2, this would be 0.025, and so therefore the value in the center part would be 0.95, because the whole thing has to equal 1, right? So if I wanted to get z of 0.05 divided by 2, just the positive value of it, I could get that also by using the inverse norm function. Let me do it over here where you can see it a little there. The light's better there. So if I wanted to know what this value was, it's just another way to skin the cat here. The area below is 0.025. So if I did second function, and then distribution, and then I go to inverse norm. The area below here is 0.025 for a mean of 0 and a standard deviation of 1. And what do I get? I'm going to get minus 1.96 for this value here. So the positive value of that is 1.96. So sometimes this positive and negative values are confusing when you're using the calculator and when you're looking at this distribution. So I wanted to show you some of the different manifestations that we can often see. Let's go down to the next one here. Change up my colors a bit. Z of 0.01, because it's a positive value, that means this is 0.01 above and this is 0.99 below. So we can get that z of 0.01, and these, by the way, these are all values that are used really common in this chapter. I can get that by going inverse norm, and then the area below that I'm interested in is 1 minus 0.01, which is a 0.99 for a mean of 0 and a standard deviation of 1. And we will find that that is, oh, we just did that one, 2.3263. We just did that one. And then finally, sometimes we're interested in an even smaller value for alpha divided by 2, and again, this should have a negative value here because it's a negative value on the z-axis. So that means that the area below here is 0.01 divided by 2, which is actually 0.005. And if I wanted the positive value of this, if it was z 0.005, then this would be 0.005, meaning that the middle part would be 0.99. And again, we can get this one pretty easily by, again, doing the inverse norm, which I didn't do up here. I better do that to be consistent here. Inverse norm, and we would say 0.005 area below, mean of 0, standard deviation of 1. So this z minus z 0.01 divided by 2 works out to be 2.5758. Negative, which means the positive value would be 2.5758. And the one up here, I forgot to mention this. So we have z minus c of 0.025 equals minus 1.96. How do we get that? Inverse norm, 0.025, comma 0, comma 1, and we got that 1.96, and so therefore z of 0.05 divided by 2 is positive 1.96. So what I wanted to point out here is that you are going to be using these values a lot. So z of 01 is 2.3263. Z of 0.005 is 2.5758. Z of 0.025 is 1.96, and then a Z of 0.05 is 1.6449. A little note about that one, I want to point that out here. Sometimes the text is not as precise as our calculators. I would rather you use the calculator value. So sometimes you'll see the text use in the text and then also in the solutions, the text uses 1.64 and sometimes 1.65. And I don't know where they go with the 1.65 because that doesn't make any sense. But I want you to use 1.6449 because it is more precise and you want the more precise value. Okay, on to the next slide. So now that we've learned a little bit about the components that go into these equations I'm about to give you, let me see here. Did I say everything I wanted to? Yes, I did. Now that I've given you everything that you need, we can look at what these confidence intervals actually look like. So as I said, we've got a two-sided confidence interval here. And another point about this first section is, even though we don't know what the true population mean is, because we don't have all the values, we are going to make an assumption that the variance of our underlying population is known. So we're not talking about Z here, we're just talking about data that we take. So what we're going to do is this is the sample mean. So remember that X bar is the sample mean, and we get that by summing from 1 to the sample size of each value of X and dividing by N. That's what X bar is. I just taught you what these Z's are. We're going to be given what sigma is, and then we'll know what the sample size is. What you should notice here is that for a two-sided confidence interval, we're looking for the subscript to be alpha divided by 2. And when we're talking about one-sided lower or one-sided upper confidence intervals, we're going to be interested in just alpha by itself. That's why they're called one-sided or one-tailed confidence intervals. So if we knew what mu was, we wouldn't be doing this in the first place. So that's an important point. So if we knew what the population mean was, we wouldn't need a confidence interval. So it's unknown. Okay, now, again, this sigma, this is going to be assumed to be known. We probably don't know it, but again, it's going to be a numerical value. And what else did I want to say here? And again, mu is a numerical value, but again, we don't know what that is. Again, a reminder that X bar estimates the population mean. So it's our estimator, remember that from chapter 6. So A little point that you should note here, and I'll put that in another color here, is that on homework and exams, I will ask you only for two-sided confidence intervals. I'm sorry, on homework, wait a minute, hang on, that's what I'm gonna say. On homework and exams, one or two-sided confidence intervals. Darn it, I'm saying this all wrong. On homework, you're going to be asked for one or two-sided confidence intervals. On exams, I will only ask for a two-sided confidence interval, just because it's what your calculator does. The other good news is if you go to the stat function in the TI series, test and then Z interval, it will actually do these equations for you. So I will do both for you here in the example that I'm about to do. So suppose that we have this situation here. We've got 5 measurements in joules of impact energy, all right? Now, it says that we're going to assume, so let's write down everything that it's giving us, right? Let me circle it here. Here's my data, and this is what I'm going to have to use to get X bar from. But they've also told me that the standard deviation of this data is assumed to be 1 joule. Now, we really don't know what it is, and honestly, in truth, I'm going to write it up here, in truth, you will never use this CI. Now, you might, I guess. I shouldn't say never, almost never, because you almost never know what the standard deviation is. So the next section that I'm going to be teaching is when we don't know what sigma is and we have to estimate it by S. But this is a good way to introduce what confidence intervals are. So we're going to do that. Sorry, I did some coffee there. Okay. So if we did this by hand, which is what I had to do when I was a young pup here, we would write down everything that we need, and we're going to get it says find a 95% two-sided confidence interval for the mean. So if it's 95% is my confidence interval, we know that that is 1 minus alpha times 100%, because we're going to need alpha for these equations. So what that's going to tell me is that alpha equals 0.05. So that's something we know. We know that the standard deviation is equal to 1 joule. And now we have this data here. Well, we also are going to need X bar. So we can get X bar really quickly if we wanted to by using the function in our calculator, that one variable statistics that I showed you back in chapter 6. So let's go ahead and just remind ourselves how to do that. If I went to, I just did that too fast, hang on a second. If I go to stat and then edit, then I can treat this like a little Excel sheet, right? So let me put the data in list 1 here. So it's 64.1 and then 64.7 and then 64.5 and then 64.6 and then 64.5. And then what I can do is I can go to stat, calc, one variable statistics. I tell it to go to list 1, which is second function, and then the 1 key here. And it tells me that X bar is equal to 64.48. So I'm going to write that down here, and that's in joules. So we have 64.48 joules. And now the only other thing that we need in this equation here, we can see that N is equal to 1, 2, 3, 4, 5. So we just need to know what Z alpha over 2 is. So Z alpha over 2, we determined that alpha was 0.05, so that's going to be Z of 0.025. And on a previous slide, we know that that value is 1.96. Remember, go back a slide here, pause this if you don't know what I'm talking about. This is the Z PDF, and 1.96 is this value right here, so that the area above is 0.025. Now we have everything we need. So my lower bound here, if I just do this by hand, is going to be 64.48 minus 1.96 times sigma, which was 1 joule, divided by the square root of n, which is 5. And then that works out to be 63 point, I'm going to take it to 3 decimal places, 603 units are joules because it is on the mean, and the mean would be in joules. Now, if I wanted to do this one, I would just add this term. So it would be 64.48 plus 1.96, 1 over square root of 5. And that equals 65.357 joules. So now I've got it. And then this is how you would present it in a meeting or to a supervisor or to yourself. You would say, based on the sample data, which is that, the probability that the interval 63.603 joules up to 65.357 joules contains the true mean, again, we don't know what it is 0.95. Now, all of this can be accomplished by using your calculator function. So let me show you how to get that. And I also recommend that when you first start doing these problems, do it by hand like this first, and then do it in the calculator, because you need to know what your inputs are so you fully understand what's happening. So here, what we're going to do is it says we're going to go to stat, tests, and z interval. All right. So we go stat, and then we go to tests, and then we go to z interval. Oh, I had z test. That was my fault. Stat, tests, and then we go down to z interval right there. And then it will prompt me. Now, I can either give it pre-crunched data or the actual data. The stats means that I would give it X bar all by itself automatically. But what I'm going to do is I'm going to have it compute it by hitting data, and then I will tell it which list to get that data from. So it prompts me for sigma, which we're assuming is 1. Again, we're assuming known. I put all of my data into list 1, so I'll go second function 1 to direct it there. And then for confidence level, I'm going to give it my 1 minus alpha value, which is 0.95. And then I'm going to hit calculate. And then what it will do is it will put up here in the upper window that first value, that 63.603, that's the lower bound L hat. And then that other value, 65.357, that's U hat right there. Don't forget what the units are. They're both going to be in joules because it is the mean. So that is how you would use this. Now, the important thing is, as I said, you're really unlikely to ever use this confidence interval. And the dirty little secret is I rarely ask for this on exams. I don't think I ever do, but I might. But here's the key. Here's how you'll know. You're going to only use this z interval or these equations when sigma is known or assumed known. And by sigma, I don't mean sigma of z, I mean sigma of the underlying data. And as I said, we usually don't know that at all. Now, we also, well, this is another thing that is kind of lost in the textbook sometimes. We're always going to assume, even though it might not necessarily be true, we're always going to assume that, the data are from a normal PDF. Now, it may not be true, but you know what? It's close enough for government work, as they used to say. If you get into, higher order statistical courses or research, you don't always have to assume that it's a normal distribution. There's ways to handle this, but this is a first course in probability and statistics for engineers, so we start out simply. Now, the next slide, and I think it is the last slide. Let me see. It is. Suppose that, here they tell you what the sample size is, right? It's 5. What if you wanted to be close to the true population mean, even though you don't know it, and you'd like to say, well, how big does n have to be if I want to be like this close or this close or this close to the true population mean? So this is how we would solve for that problem. It's really quite clever here. So let me point out some of the wording here. So suppose we want our estimate of mu x bar. Remember, we don't know what mu is, but x bar we can get by getting the sample mean. We want it to be less than a specific distance from the true value. In other words, we want to be this confident that mu minus x bar, the absolute value, is not more than E. So either we're going to choose this letter E, or the book does, or I do, right? So E is our desired absolute difference between the mean, true mean, and the sample mean. So again, this is an actual value. So is this that we compute. And this is an unknown, but it is an actual value. What you're going to be given is the actual value of E. So you'll be given E in a problem, just like the one down here. So let's suppose it was the previous example, okay? So suppose that your boss says to you, hey, how big should N be if we want to be close within 0.5 joules of the true population mean? So E here was given to us as 0.50 joules. See, we don't need to know what mu is in order to be have a desired E, okay? We know that alpha is 0.05. We figured out that z of alpha over 2, which again was the z of 0.025, that was 1.96 from the previous problem, and they gave us that the population standard deviation was 1 joule. So how many samples would we need to take if we wanted to be within 1/2 a joule of the true population mean? So here's how we would do it. N equals z of alpha over 2, 1.96, multiplied by sigma, which is 1, divided by E, which is 0.5, and then we take that whole thing and square it. And what you'll find is that works out to not be a whole number. It's 15.4. So we can't take 15.4 samples, so we're always round up, no matter what, even if it's not over 0.5 here. So you always round up. So when you do your homework problem that is similar to this, you would round it up to 16 and you would enter that as your answer. So you would choose 16 items or 16 samples if this was your desired closeness to the true population mean. Okay, here endeth this little lecture.